Welcome to EDU World Space.
Okay, in this problem we have an object that's 4.5 centimeters tall, located 26 centimeters from some kind of spherical lens, some kind of mirror, and we want to ultimately produce a virtual image that's 3.5 centimeters tall. We're first asked what kind of lens, what kind of mirror would we need to use, and what are everything else we can learn from this problem, essentially the image distance, the focal length, and the radius curvature of the mirror. So we're asked a number of things. These all can be accomplished with a little bit of ray tracing and the main lens equation, 1 over d naught plus 1 over di equals 1 over f, where f is the focal length and di and d naught are the distances from the lens or mirror for the image and object respectively. We also know the fact that the radius curvature is 2 times the focal length. That's always the case for lenses and mirrors. And we may need to use the definition, the fact that the ratio of heights is also equal to the negative ratio of distances, which has been proved in a previous problem. So to start us off, in order to produce a virtual image that is smaller than the original object, we need to use a convex mirror. So that can be answered immediately. It's always the case that to produce a smaller image that's virtual, we need a convex. Now the rest of these are quantitative, so we're going to have to make use of our equations. So we can do that. We can start by using m, as I invoked earlier. It's the ratio of heights. It's also the ratio of distances. Here, this is looking a little messy. We can deal with that. There, ratio of heights or negative ratio of distances. We know the height. We actually know both heights. The desired height of the image is the actual height of the object, and the height of the distance of the object. So we really need to solve for one thing. We can solve for the image distance, which is simply d naught times hi over ho. We know everything, so we can calculate this as, negative sign, of course. So we have a negative 26 centimeters times 3.5 centimeters all over 4.5 centimeters. These are all given, which will come out to be negative 20.2 centimeters. So that's one result. That's the result for B. Now to find the focal length, we can use the lens equation, also valid for mirrors. 1 over d naught, or do rather, plus 1 over di equals 1 over f. We know di, we know do, so f with a little bit of algebra is d naught times di over d naught plus di. Plugging in our numbers, we end up with negative 90.55 centimeters. Okay. And lastly, we can just make use of the fact that the radius curvature is always twice the focal length. So it goes without saying that it will be roughly negative 180 centimeters. And that's everything we can know about this problem, essentially. We solved for pretty much everything using all the equations we know. So just to recap, we use the definition of magnification and the ideal lens equation in conjunction with the fact that the radius curvature is always twice the focal length, and we solve for everything. And that's it.